everyone. In this lecture, we'll explore hierarchical software architecture, a structure that helps us organize complex systems into manageable levels of logical modules, or subsystems. Let's start with a basic understanding. In a hierarchical architecture, we build our system in layers, where each layer serves a specific role and connects logically with other layers. This structure allows us to separate concerns, which makes our system both scalable and easier to maintain. Now, let's dive into module interaction within this architecture. The key idea is that lower-level modules provide essential services to upper-level modules. Think of it as a chain of command, where each layer builds upon the functionality provided by the layer below it. For example, in a banking application, the lowest level could handle basic database interactions, while the next level up might manage business logic, like transferring money or processing payments. The highest level would be the user interface, interacting with the business logic to show the user's transactions or balance. The communication between these modules happens through method invocations, which we can organize in different ways. Procedural approach: in procedural programming, functions and procedures are usually defined in headers or libraries. The higher levels call these functions directly, passing data back and forth. Object-oriented approach: with object-oriented design, we structure services as classes organized into packages. These classes interact with each other through methods, allowing for modular and reusable code. In practice, upper-level modules will call functions or classes from the lower levels to make use of the services they offer. This approach helps keep each module focused on its responsibilities, reducing dependencies and creating a clear flow of information from the lowest level up to the top. By the end of this section, you should understand how hierarchical architecture helps to create well-organized, scalable, and maintainable systems. In our next slides, we'll look at some practical examples of how this architecture can be applied in real-world systems. Now that we've covered the basics of hierarchical software architecture, let's look at where this approach is commonly used and how the layered structure functions. Hierarchical software architecture is widely adopted in foundational systems where different layers play specific roles in providing reliable services. For instance, Microsoft.NET. This framework uses layers to separate application logic, services, and system utilities. Unix operating system layers here provide a structured approach to resource management, user interfaces, and process control. TCP/IP protocol stack. Each layer in TCP/IP has a unique function, from basic data transport to application-level protocols like HTTP. These examples highlight how hierarchical layering helps these systems maintain efficiency, reliability, and ease of maintenance. In hierarchical architectures, each layer has a well-defined responsibility, organized from the most basic utilities at the bottom to high-level interfaces at the top. Let's break down these layers. Lower layers, these are responsible for fundamental utility services, such as input, output operations, transaction management, task scheduling, and security. These form the backbone of the system, offering essential functions that other layers build upon. Middle layers, this layer focuses on domain-specific functions, such as business logic and core processing. Think of this as the heart of the application, where the main functionality takes place. For example, in a banking application, this layer would handle financial transactions, calculations, and business rules. Upper layers, finally, we have the upper layers, which deliver abstract and user-facing functionality. This includes graphical user interfaces, GUIs, shell scripting, and other components that interact directly with the user. The upper layers depend on the services provided by lower layers to display data and manage user interactions smoothly. One of the biggest advantages of this architecture is that each layer affects only the layers directly adjacent to it when an interface changes. So, if we update a function in a lower layer, only the middle layer might need adjustments, not the entire system. This minimizes ripple effects, reducing the potential for unexpected errors across the application and making the system more adaptable to change. In this section, we'll take a closer look at the hierarchical software architecture, which is a structured approach that organizes a system into a hierarchy of levels. At its core, hierarchical architecture is designed to create an organized structure where each module has a specific role. Each module provides services to the module directly above it and relies on services from the module below it. This top-down organization forms a clear chain of responsibility and dependency, making complex systems more manageable. This architectural style is commonly seen in well-known software systems and class libraries, such as the Java API and .NET namespaces. In these libraries, we see distinct hierarchies that allow for organized, reusable code across applications. Let's discuss some defining characteristics of hierarchical software architecture. Hierarchical structure, the structure itself is a hierarchy, which means it's organized into different levels. Modules connect through a call and return connection style, where each module either calls upon lower modules or returns data to the ones above it. Versatility across design approaches, hierarchical architecture is versatile enough to be used in various design methodologies. It supports procedure-oriented, object-oriented, and even component-oriented designs, allowing it to adapt to different development approaches based on project needs. Combining with other architectural styles, this architecture is often combined with other styles to enhance specific functionalities. For example, a layered hierarchical system might integrate elements from a microservices architecture to allow better separation and scalability. Hierarchical architecture is not a one-size-fits-all model. It has different variations to suit specific use cases. Main subroutine, this style is common in procedural programming. One main routine calls subroutines to complete tasks, following a structured top-down approach. Master server, here, a master module controls multiple server modules. This style is useful in distributed systems where the master delegates tasks to servers. Layered architecture. This is perhaps the most widely recognized style, where layers are organized from basic services at the bottom to user-facing functionalities at the top. Virtual machine, in this style, each layer is essentially an emulator of the layer below, creating a self-contained system within another system. This is often seen in platforms that support virtual environments. Next, let's explore the main subroutine design architecture, a traditional and foundational software design style that paved the way for many modern programming paradigms. The main subroutine architecture was widely adopted before object-oriented programming became mainstream. This design style structures the program with a main routine, which serves as the central control unit, and a series of subroutines that perform specific tasks. Each subroutine is independently developed and can be reused across the application, making it an efficient approach for organizing code. The primary goal of this architecture is to promote the reuse of subroutines. By separating functions into distinct subroutines, developers can create reusable, modular code that can be called by the main routine or other subroutines as needed. This modularity allows for efficient development and testing, as each subroutine can be worked on independently without affecting others. Let's look at some important characteristics of this design style. Procedural paradigm. In a procedural programming environment, subroutines often share data among themselves at the same level. Variables and data structures are passed between subroutines, enabling shared access but increasing the risk of unintended data modifications. Object-oriented paradigm. While less common, main subroutine architecture can also be adapted for object-oriented programming. Here, data is encapsulated within objects, which enhances data protection. This approach prevents direct data sharing, as each subroutine accesses data only through controlled interfaces. Classical against modern design, main subroutine architecture is viewed as a classical approach in contrast to object-oriented design, which emphasizes data encapsulation as a core principle. In object-oriented design, data and the methods that manipulate it are bundled together within classes, while the main subroutine model typically separates functions and data. Building on our understanding of the main subroutine design architecture, let's dive into how this design is refined and why it supports modularity and maintainability so effectively. In the main subroutine design architecture, the software system is initially decomposed into hierarchical subroutines. This means that the system is broken down by functionality, with each subroutine addressing a specific task. To ensure each part of the system has a clear responsibility, vertical refinements are made. This refinement process continues until each subroutine is fine-tuned to handle a distinct, independent responsibility. For example, in a payroll system, the main routine might call subroutines for calculating wages, deducting taxes, and generating payslips, each further broken down into smaller, focused tasks. Once refined, these specialized subroutines can be reused and shared across different parts of the program. For instance, a subroutine that calculates tax deductions could be called by multiple modules, like payroll and financial reports. This reusability not only reduces code redundancy, but also makes the software system easier to understand and modify. Because each subroutine operates independently, changes in one part of the system are less likely to impact others. This modular approach enhances maintainability, making it simpler to update, test, or replace individual subroutines as needed. In summary, through a process of decomposition and careful refinement, the main subroutine design architecture enables a well-organized modular system. Each subroutine has a distinct purpose and can be reused as needed, supporting the goals of modularity and maintainability. In the upcoming slides, we'll look at practical examples where this architecture style benefits software development, particularly in systems with repetitive or shared functions. As shown in Figure 702, the main subroutine architecture organizes the software system with a main program at the top, which controls the sequence of subroutine calls. This structure is designed to support modularity and efficient code reuse. When data needs to be sent to subroutines, it's often passed through parameters. There are two main methods of parameter passing. Pass by reference. In this method, the subroutine receives a reference to the original data, allowing it to modify that data directly. This approach is useful when the subroutine needs to update or affect the original data. Pass by value. Here, a copy of the data is passed to the subroutine, so the original data remains unchanged. This method is ideal when you want to protect the integrity of the original data and prevent any unintended modifications. Additionally, parameter passing by name is also possible, though it's less common in modern programming. This approach allows data to be evaluated as an expression, giving more flexibility, but it's not widely used due to complexity. In this architecture, the main program controls the sequence in which subroutines are called. This is often done through loops or specific invocation orders, allowing for a structured flow of execution. For example, the main program might call sub1, then sub2, and so on, following a predefined logic or dynamic conditions. One of the biggest strengths of this approach is subroutine sharing across the hierarchy. By refining subroutines to handle specific tasks, they can be reused by different parts of the program, promoting modularity and reducing code duplication. In this part of the lecture, we're going to discuss data flow diagrams, or DFDs, and see how they can be mapped into a main subroutine structure. A data flow diagram is a visual tool used to model software requirements. It helps us understand how data moves through a system, highlighting the relationships between different processes and data stores. DFDs are especially useful in early stages of system design, allowing us to visualize and refine system requirements before diving into detailed coding. Let's go over some of the key symbols used in a DFD. Bubbles or circles, these represent processes or activities. Each bubble indicates a specific function or task, such as recording customer information, validating a purchase, or handling a return. Arrows, these arrows indicate the flow of data between processes, showing how information moves from one task to the next. For example, data flows from the customer to process number one recording information and continues through the system. In this example, we see a DFD illustrating a purchase order processing system. It starts with customer input, which flows through a series of validation and decision-making processes. Each process has a distinct purpose, and data flows between them to complete the transaction, whether it's a purchase or return. Below the DFD, we see how it's mapped into a main subroutine structure. Here, the main program controls the sequence, invoking each subroutine to handle specific steps in the process, such as Process 1, recording customer info. Process 2, validating information. Processes 5 to 8, handling actions like purchasing or returning items. This DFD can be directly mapped into a hierarchical structure, as shown below. Each numbered process corresponds to a subroutine in the main subroutine architecture, with the main routine at the top managing the flow. The DFD helps us identify and isolate the functions we need, making it easier to implement them as separate subroutines in the final program. Now, let's take a look at two major types of information flows commonly seen in software architecture: transform flow and transaction flow. Transform flow refers to information flow where incoming data is transformed into a different format before being outputted. This is especially useful when we need to convert data for compatibility with other systems or processes. Example, suppose we have incoming data in XML format. In a transform flow, this XML data might be parsed, processed, and then transformed into a JSON format or another required format before being sent to the next process or application. Transform flow is typically used in systems where data conversion or processing is a key function, such as in data integration platforms, ETL, extract, transform, load systems, or APIs that aggregate information from multiple sources. Transaction flow, on the other hand, is driven by specific events or user actions. This type of flow manages the control path based on events or transactions initiated by the user or the system. Example, in a banking application, when a user initiates a transaction, such as transferring money or checking account balance, it triggers a specific flow. This transaction flow follows a defined path that depends on the action taken. For instance, if the user initiates a transfer, the system will validate the transfer details, check for sufficient funds, process the transfer, and update records accordingly. Transaction flow is essential in applications where user interactions determine the system's actions, such as in e-commerce, online banking, or interactive web applications. In this part of our lecture, let's discuss how we can map a data flow diagram DFD to the main subroutine design architecture, allowing us to systematically design software that meets specified requirements. In the main subroutine design, each process in the DFD corresponds to a subroutine or module in our hierarchical design. This means that each individual task or function shown in the DFD is implemented as an independent subroutine. By creating a one-to-one mapping, we ensure that each requirement from the DFD is directly addressed in our code, providing clarity and modularity. The DFD's sequential flow of data aligns well with the top-down approach of the main subroutine architecture. As data flows through each process in the DFD, it moves down the hierarchy in the main subroutine structure, allowing the main program to control the sequence and order of subroutine calls. This clear sequence helps in building an organized, easy-to-follow program structure. We can further classify subroutines based on the type of flow they handle. Transform flows, these map to subroutines that handle data transformations. For example, if a DFD process involves converting XML data to JSON, we can create a specific subroutine to handle this transformation. This approach keeps our code focused and organized. Transaction flows, these map to subroutines that manage event-driven operations. For example, if a DFD process handles user-initiated actions, like checking an account balance or making a purchase, we create a subroutine that responds to these specific events, ensuring a smooth and controlled transaction flow. By mapping each DFD process to a corresponding subroutine in the main subroutine architecture, we ensure that the software design systematically fulfills all specified requirements. This approach not only helps in organizing the code, but also provides a clear traceability from requirements to implementation. In this section, we'll explore how to map transaction flows and transform flows to the main subroutine design architecture. We'll look at the mapping steps, the role of transform flows, and how factoring analysis helps refine our design. Transaction flow refers to an information flow where incoming data is evaluated. And based on specific conditions, one of several action paths is selected. This flow is event-driven, reacting to specific inputs to determine the appropriate response. Mapping steps for transaction flow. Identify transaction and transform flows. Start by analyzing the data flow diagram DFD to determine which processes represent transaction flows event-driven and which represent transform flows data transformation. Separate incoming path from action paths. Differentiate the initial input path from the various action paths that data can take. Classify each action path. Label each action path based on its function, identifying whether it follows a transform or transaction flow. This helps us map each action to a specific subroutine in the hierarchical design. Transform flow, on the other hand, is concerned with the overall flow that transforms data from one format to another. This flow is primarily used for data processing rather than event-driven actions. Mapping transform flow. 1. Isolate the transform center. Identify the central transformation process in the flow. This process acts as the core transformation module. 2. Assign a controlling module. Designate a controlling module responsible for managing the incoming data, processing the transformation, and directing the outgoing data. This module will coordinate the flow and ensure data is processed correctly. To enhance modularity and maintainability, we perform factoring analysis. This involves repeatedly decomposing each module until it has a single specific responsibility. By breaking down modules into smaller units with distinct roles, we create a well-structured architecture where each module has a clear purpose. Benefits of factoring analysis. Ensures each module fulfills a specific role, which simplifies testing and debugging. Promotes reusability, as each module can be repurposed in other parts of the system or in future projects. Enhances clarity in the architecture, making it easier for developers to understand and maintain. Let's now take a closer look at the concept of a transaction center and how it manages a purchase process within the main subroutine design architecture. In a hierarchical design, the transaction center acts as a control module. Its role is to evaluate the type of transaction and then direct the flow of data to the appropriate action modules. Think of it as a central hub that decides the next steps based on the specific transaction type. To illustrate, let's walk through an example of a purchase process that uses the transaction center to handle customer requests. Process #1. Receives and records requests. The transaction begins with process #1, which receives and records the customer's request, whether it's for a purchase or a return. Process 2 validates requests. The request then moves to process 2, where it's validated. If the request is invalid, it's sent to process 4, which handles rejections by notifying the customer of any issues. This ensures only valid requests proceed in the system. Process number 3 chooses an action path once validated. Process number 3 acts as a decision point, directing the request to either the purchase path or the return path based on the customer's needs. Purchase path. Process number 5, check stock. First, we check if the item is in stock. Process number 6 verifies credentials. Next, we verify the customer's credentials, such as payment details or account status. Return path. Process number 7 checks return policy. For a return, we check the return policy to confirm eligibility. Process number 8 handles refunds. Finally, we process any eligible refunds. This step-by-step transaction process creates a clear hierarchy, as shown in Figure 7.3. Each process has a well-defined responsibility, forming a structured path for each transaction type, whether it's a purchase or a return. This hierarchy ensures that each module performs a specific role, making the system organized and easy to maintain. Let's quickly go over some benefits and limitations of the main subroutine architecture. Benefits. This architecture is straightforward to decompose. We can break down tasks easily using a top-down refinement approach. Despite being a traditional design, it can still be used as a subsystem within an object-oriented OO design, providing flexibility in hybrid architectures. Limitations. The use of globally shared data in classical main subroutines can introduce vulnerabilities, as data is accessible across multiple modules. Tight coupling in this design means that changes in one module can have a ripple effect, making the system more sensitive to changes compared to OO design, where encapsulation reduces this risk. In summary, while main subroutine architecture is useful for organizing tasks, careful attention is needed to manage data sharing and coupling. Next, let's discuss the master-slave architecture, a design structure that enhances fault tolerance and system reliability by distributing tasks across multiple components. The main purpose of this architecture is to support fault tolerance, ensuring the system can continue operating reliably even if some components fail. This is especially useful in critical systems where uptime and accuracy are paramount. In this architecture, we have two main roles. Master. The master module controls and coordinates tasks across the system. It's responsible for collecting results from the slaves and selecting the best outcome based on specific selection strategies. Slaves. The slave modules provide replicated services to enhance reliability. They may perform identical tasks using different algorithms to verify consistency, different functionalities altogether to cover various aspects of the task. Here's how the process works. Master invokes tasks. The master initiates tasks by sending them to all slave modules. Slaves process and respond. Each slave processes the task independently and returns a result. Master evaluates responses. The master then evaluates all responses and selects the most suitable result, ensuring the best outcome based on the system's reliability needs. This diagram illustrates a UML class structure for the master-slave architecture, showing how the components work together to enhance system reliability and accuracy. Components. Master. The master class delegates tasks to multiple slave classes and then evaluates their responses to select the best result. Slaves. Each slave class provides the same service but with a different implementation. This approach allows us to use various algorithms or methods, ensuring diversity in processing. Characteristics. Parallel execution. All slave classes can operate in parallel, which significantly improves efficiency and reduces processing time. Accuracy and validation. By using different implementations, the system can validate results through strategies like majority voting, enhancing the accuracy of outputs. This structure boosts fault tolerance by having multiple implementations handle the same task, ensuring that even if one fails, others can provide accurate results. It's an effective way to maintain computational accuracy and reliability. In summary, the master-slave architecture leverages parallel processing and diverse algorithms to create a robust and fault-tolerant system.